Alrighty. Morning, everyone. So we're going to change gears a bit. Instead of looking at some pretty pictures, we're going to sort of start to look at some structural geology and sort of the next step from what we can sort of do with that. And really, what this project started a while ago was just to sort of try and value add based on some of that really high resolution new data. And it really is a big step change. So I'll just sort of guide you through a bit of some of the insights from there. So first, I apologise for the non-structural geologist, but yeah, just to sort of go over some of the basic structural geology 101 sort of stuff. And so here you can see a couple of block diagrams, basic sort of good old Andersonian faulting. Typically quite simple relationship between stress and strain, but it's for ideal fault relationships and it's an isotropic media. And we know that faults aren't always ideal, and the lithosphere is highly anisotropic, especially where we've had previous deformation. So apart from your three sort of end-member faults, you've actually got transpression and transtension, which are sort of between those sort of regimes. And you can really think of it as a continuum. So at sort of low angles of obliquity, so at low alpha, which is at 0 alpha, you've got strike slip. At low alpha, faults behave more or less like strike slip. At higher angles, you start to get more complex networks of strike slip, dip slip, oblique slip faults. Strain partitioning is really common in these sort of things. So quite commonly, you sort of partition out the simple shear, which is blocks sliding past each other, and pure shear, which is just a sort of more sort of squishing. So just to look at the transtension transpression, so the diagram on the right here is essentially just some schematics of some strike slip faults, and depending on the kinematics, whether it's dextral or sinistral, and the direction of maybe of fault steps where separate fault strands are separated, you can get these zones of extension or transtension, and these zones of contraction or transpression. And so these you can have these sort of manifest in a number of ways. So you can get sort of flower structures, either positive or negative. You can get pull-apart basins and pop-ups. And you can also get strike slip duplexes and things like that. So it starts to get really kind of funky when you start to sort of partition strain across these complex networks. And the diagram on the left there is just a simple sort of one of a fault in a thrust system. And I know we always like to sort of see a thrust in the old bow and arrow rule and transport's perpendicular, but you get sort of complexities there as well with these sort of lateral ramps and oblique ramps. So again, that's sort of, more sort of transtensional sort of things. So in real life, things get weird, and we need to measure lineation. So please, I wish that I had more lineations to take into account on this interp. So moving forward from all that, where I started with this project was sort of apart from looking into the new data, trying to understand the large scale framework. And this is actually an approach that Karen sort of takes using the seismic sort of interpretation, and it's something that I've tried to do, but in the map view as well. So the way I see these sort of large scale, these large structures that I sort of really recognise here is that you've got the Kalkadoon-Leichhardt crystalline basement, this dark blue kind of belt running through the middle, and you've got the Leichhardt River fault trough to the west of that, this is a rifting axis, so it's during the sort of Leichhardt super basin, and so those bounding structures are sort of rift margin sort of type things. What we also sort of see is that these northeast southwest striking normal faults, and these are usually sort of interpreted as they're most obvious because they get reactivated during the late Isan, and they cut across quite a lot of the structures. But they actually cut across some barramundi basement through here, and they're cross-cut by mid-Isan, the main Isan Orogeny north-south structures here. So we've got things which are older as well. And some of these sort of really big lithospheric scale structures like these, you know, they're often sort of, you know, quite cryptic. And so you see these zones where, you know, you see fault segments kind of, you know, sort of disappear and reappear as you sort of go. And just at the bottom here, there's some of the other things that I've been sort of looking at is analog modeling. So here's a couple of one on the left is an analog model of sort of what happens when you sort of extend. So this little block is extending northwest to southeast, and you see the sort of these second order structures. Well, you see these structures here, which is just normal, and then you start to partition a greater amount of extension in these zones of weakness here. So you've got an oblique zone of weakness. Here's a numerical model, and it's again similar sort of setup where you've got this sort of relatively high obliquity. And again, you see these second order structures within the main sort of rift zone here are sort of reflecting that far field extension direction within an overall kind of within the main sort of zone of deformation. So from there, I want you to think about what will happen to these big structures during the Isan orogeny. So I'm using the Hinman and the deep mine in Queensland and the Northwest Queensland structural sort of evolution. You know, it basically follows more or less the main recognised one. But I'm using this for the extension directions, the far field sort of directions. So D1, you know, I don't think it's contentious. We've got north-south, sort of north-northwest, south-east thrusting. And this sort of resulted in sort of a, you know, folding of the cover sequences. And this was sort of really local, like, so folding of the cover sequences, and in the eastern fold belt, you've got north-northwest directed thrusting and nap formation. So keeping in mind that we've got sort of, previous to this, we had a large sort of thin back arc, you know, quite hot. You know, we're gonna sort of reverse all of those northeast southwest striking faults, the early architecture that was related to the extension, and we might also get some sinistral reverse on these north-south structures. Skipping forward to the main Isan east-west, and so you've got a thick-skinned deformation, and this is really sort of like progressive basement-involved shortening. We don't get any high pressure rocks, so we've got modest crustal thickening, and this is really common in those high geothermal gradient Proterozoic origins. And lots of north-south trending folds and thrusts. This is the Isan that we all know and love. So what we also sort of see is that we've got these northeast southwest striking faults, and we're going to get dextral or dextral oblique motion on those, and reverse on north-south sort of faults. And one of the things that I picked up in the data is quite a lot of sort of transpressional sort of structures throughout the main belt of the Mary Kathleen and Chalcodon Leichhardt belt. Skipping to late Isan, to Isan D3, so this is where we've got those sort of relatively large dextral offsets on these northeast southwest faults. Again, we recognise transpression, but it's much more of a wrench component here. And following some of these structures through, you start to see escape towards the south. Some of these faults sort of terminate in some sort of thick-skinned thrust. So we've got sort of these steep structures in the hanging wall of some of these decollements. So there we go. These northeast southwests become dextral, and we might get north-south faults. We've got dextral oblique on those guys. So we're really seeing this history of these faults getting activated and reactivated again and again. The latest Isan we see in the eastern fold belt, it's northwest to southeast, and this is sort of, you know, associated with that brittle ductile transition, lots of brecciation, mineralization, lots of fluids around, and so we've got a lot of fluid overpressure here, and I think that's one of the things that drives some of this later reactivations as well. So getting into the Landsborough Graben here. So this is just in the eastern margin of the Mary Kathleen domain. You can sort of see some of the main the mines and deposits there. And the geometry of the Landsborough Graben is that we've got these sort of bounding faults, and they converge downwards. So the western fault dips east, and the eastern fault dips west. And so these can be interpreted as where you've got these northwest, just in here, you've got like a bit of a step over between the Mount Roseby fault on the right and the Pinnacle fault on the left. So we know these faults were active in the Isan, not just the late Isan, sorry. We've got sort of the Roseby schist belt sort of running up through through both arms along parallel to these faults. And we also see some post-Mesozoic activation in these. So there's a couple of 100 meters of offset in the Jurassic rocks there. And we probably don't see that in the Cambrian. And that's really that the facies variations within the Graben sort of aren't really reflecting something that's sort of depositing next to an active sort of fault scarp. So, and we also sort of see some of these shortcut sort of structures where we've got the Kulala fault is on the eastern part. We've also got this unnamed fault that cuts through the middle. And we've made lots of observations of sinistral and sinistral oblique deformation through there. And what the mag sort of shows us here is we've obviously just got sort of, you know, we can sort of see some of the map view things, but and we can see some longitudinal sort of, some differences along here. So we've sort of got some of these anomalies which interpreting as sort of basement sort of highs. And we've got sort of areas where the basement is sort of more subdued, and so the interpreting is deeper parts of the basin. And we've also and we can sort of see some of these these transverse structures as well. So the image on the right there is the 1VD in the background, and it's we're looking sort of steeply towards the north now, so it's slightly sort of tilted. And the sections you're seeing there are some of the IP sort of corrected resistivity sections, and you can see that this is where we can sort of see some of the dips of the structures, and we can sort of start to image the basement beneath the fault. So the Landsborough Graben, it was explored sort of, the margins have been explored sort of quite a lot, and I think there's current tenure all around it, but there's not a lot in the middle. And back in the 70s, BHP, they had held a prospect over it and drilled a couple of holes looking for Dugald River style sort of you know, SEDEX base metal mineralization. They found pretty modest, not too great phosphorus, and they didn't find much sort of lead, zinc, or copper. And they actually, so here's some of the drill holes. And you can sort of see that you saw in here. So from left to right, you sort of go stepping from the western margin, you go south, and then you've got these 3 drill holes in the middle. And they looked at the dips of the strata and thought, you know what, it's going to be more than 600 meters deep in the east. There's no point. We're not going to find anything. It's too deep. And they were really sort of basing this on this modest easterly dip and this sort of half Graben sort of model for the basin. But looking at some of these analog models, and here's one by Sugan et al., just looking at a dextral releasing dextral releasing bend here, and you can see this little pull apart basin forming there, and the cooler colours are more subsidence, so you can see higher subsidence in the middle. So this is very different from you know, a half Graben sort of model. And you can see these sort of, again, these transtensional sort of regimes. So you've got strike slip, normal, and oblique slip. And these are compartmentalizing sort of the basin fill and also the sort of subsidence. And you'll notice there's a set of shortcut faults cutting straight through the middle of that one. So I'd posit this is a better model than a half Graben for the Landsborough. And yeah, so this is the sort of thing that I think we probably might be looking at if we were going to try and sort of interpret the sort of structures. So, so what we see in the Landsborough Graben is we've got the drilling that BHP conducted. This is BHP4 here in the northwest. This is where they actually intersected basement at 260 meters. And you can see that actually this is in a sort of a subdued magnetic sort of domain. So this is even quite sort of deep. I'd imagine this is quite a shallower basement area. And right in the middle here, if you recall, this is where you've had the maximum subsidence. And in this corridor, this is where BHP put their 3 holes. So we've got sort of 260 meters in the northwest. Some of the work out of Copper Mountain is coming out at less than 300 meters in the eastern part. And so these flanks are probably at really accessible depths. So just to sort of put the Landsborough Graben in a slightly bigger context. So the image on the right there is really just, you know, the good old sort of get your scissors out and chop up the late faults. And it's quite nice because you can see it actually reconstructs quite a number of things, these sort of belts of argilla, the sort of OD would have called the argilla detachment. It reconstructs things like the sort of Wonga belt. And if we go up to the Landsborough Graben sort of here, you can see the black line that I've drawn in there, which is the Pinnacle Fault here on the west. And it reconstructs here to a similar sort of domain across the Mount Remarkable Fault. And then here in the far sort of north, I think it sort of comes along through this one. So the image in here is the new magnetics with the depth of basement drilling that was in a product that we released, I think, earlier this year. And you can see, so the color scheme here, which I forgot to put a legend on, is that your yellows are around the sort of 100 meters. At around between the transition between red and purple is around 200 meters there. And once you get into the really light pinks, you're in you know, more than 300 meters. And so what we can sort of see is that this sort of part immediately sort of the first northern continuation is really quite sort of you know, reasonably shallow, you know, sort of at around sort of 200 meters, deepening as you go further and further to the northeast. So again, yeah, this sort of confirms we're not looking at 600 meters here in the Landsborough Graben. It's probably quite a lot shallower. So I hummed and hawed about what I wanted to show everybody, and without sort of taking you all on a journey through ArcGIS and zooming in and out, I think so. I thought I'd just take a couple of snapshots of some areas where we found some interesting new things in the data. So here's the western margin of the Landsborough Graben, and you can see the overview map on the left. And then the next map over is the current 100,000 solid geology. You can really see it's quite a simple, you know, homoclinal sequence almost, with the Lime Creek metabasalt there in the green, the Wonga belt to the left, and then the Corella formation out to the east. If you you can see the magnetics there, so that's the RTP with a 1VD and a multi-directional hillshade, and it really pulls out some you know, a huge amount of structure in there. And you've got the sort of the new interpretation over there to the right. So see lots of folds, even the Lime Creek metabasalt, which is this sort of this kind of darker area. You actually can see in some of the radiometrics and in the high resolution ground air photos, you can actually pick up lots of little sort of veins and dikes, and some of them look like they could be folded as well. So we're looking at kind of a couple of high strain sort of corridors here between the Wonga belt and the Landsborough Graben. So just yeah, sorry, this box here just sort of far to the south. This is the southern extent of the Roseby, and this is the area for the next slide. So as you can sort of see here, we've got a huge amount of sort of complexity in there, with the Roseby schist sort of running down through the middle. And in the western sort of zone, this quite red zone, you've got the Godkin granite in the north, and Mount Birstall to the south, and you've got this strain shadow in between where you can see really kind of nice Isan D2 folds. If this is the interpretation that we start to see that I've made, and the Roseby belt is really sort of a lot of dextral and sort of transpressional deformation related to the sort of main and late Isan. Interesting, in the latest Isan, the D4, D5s, we see some of these brittle conjugate sort of faults sort of up against the west, up against the Cameron fault here. We also see in through this region here, we see quite a lot of sort of syn kinematic kind of pegmatite or felsic sort of dikes, and a couple of sort of there it is. And a couple of these sort of possibly, they might be related to some of these interpreted blind intrusions. And interestingly, we have the Lakeview dolerite, which comes up through here, and it's quite linear to the southwest, but here you actually see it starts to take advantage of the fault network. So it's quite a yeah, sort of an interesting sort of area to sort of have a look at, and there's definitely some areas where it would be worth having another look at. So I've had a couple of extra slides talking about some of the changes to the redefinition of the western boundary of the Mary Kathleen domain. I'll just flick back and forth between those, but really this is sort of coming out of this is coming out of some of the geochronology that work that we did in the south. We've got a lot more of the Chalcodene Leichhardt belt to the east, in the south, and then some sort of I guess just a bit of a refinement to the west. There's also a lot more sort of Agilla age intrusives in the western Wonga belt as well. So yeah, there's some of the sort of broader Mary Kathleen domain sort of outputs. And I'll leave it there. Thank you. Questions?
Questions? Do we have any questions for Derek?
I'll ask the question.
Okay, Paul. Oh.
Thanks, Derek. How do you know that all those faults that you're drawing in Isan?
Sorry, say that again?
So that one picture you showed there, northeast of Mary Kathleen, how do you know all these faults you're drawing in Isan faults?
Yeah, that's...
And that network you're drawing is an Isan Orogeny network.
It's a good question. Yeah, I know where you're going with it. Again, here we're just sort of going on the published sort of thing. So until we actually go through and date a lot of these sort of minerals, yeah, we're not going to know. They could well be earlier. The Wonga sort of age, or Strangways, this Wonga orogeny, they definitely could be. In different areas, it gets quite complex. Sometimes you see faults which should be late, seem to be quite early. So yeah, when you get into the details, some of the overprinting relationships, it opens up a lot of possibilities. Yeah, with more time and sort of, definitely, could work in that space.
Hi, Derek. Two questions, I guess. The first one is similar to Paul's. Is there a program of validation of this work, either being completed or in progress, ground validation? And then the second question is actually just technical. What did you personally find were the best filters to use for the interpretation?
Yeah. So in terms of field validation, you can never have enough. We have gone to the field 2-3 times. I think spent about a month in the field, which is still woefully inadequate for such a large area. And that was really just focusing on the Roseby corridor itself. So yeah, there is quite a lot of ground validation. That was really just aimed at trying to assign geology to, what are just sort of, changes in magnetic intensity. So there has been, and there will be, we'll get into that in the report that sort of will come out. On the technical question, some of the filters that I found to be really useful. Personally, I think I'm not a big fan. Obviously RTP 1VD. Looking at the RTP works quite well. There's not a huge amount of remnants in a lot of the rocks. There's some subtle remnants, but not sort of terrible. So that's quite sort of it's reasonable to interpret. Doing sort of a mix of 1VD. I find the tilt angle is a good one, because you get that short wavelength features, but also from deeper in the crust, so not just the shallow. So the 1VD really highlights the shallow stuff, not the deep stuff as well. And I've always been one of the things that I've found more recently is is in ArcGIS Pro. You can sort of turn on the dynamic range, so you can have that based on the view extent. And that's really important, because some of these things are extremely high, but these screaming high anomalies. But because we've got this new data, it's extremely high precision. So you can actually pick up these very subtle anomalies. And if you've got them all on one color stretch in an image, it doesn't work. So that's really important. And the multi-directional hillshades, I think, are another good one, which kind of helps the eye sort of follow structures and trends a bit better than, say, just a 1VD or something like that, which can just look a bit flat. So, yeah.